Good morning, Year 13. How's it going, guys? It's nice to see you. We've only got Emma missing now in the chat. I figured I just wouldn't start straight away. I know we're now like 4 minutes in, which is a bit frustrating because I figured it could have been quicker than that. But with just missing Emma now, I feel like I'm just going to crack on now. I'm just going to mark her as missing for the time being and then update it when she now appears. Right, okie dokie, guys. I need to reduce my, okay, auto. Take that light down. Okay, right, guys. She declined my call. Oh, there she is. There she is. Cool, we have a full house. Amazing. And get rid of the reg. Right, fab. Okay, guys, let's just crack straight on. So I'm going to share my screen and we can get on. You notice that the learning objectives on the YouTube video, I kind of hope that you guys are kind of getting used to this now. I know that I certainly am trying to. I'm also trying to very carefully number my lessons these days. I think I need to go back and edit one, actually. I was meant to do that yesterday. Okay, so A2 Equilibria lesson 3, moles at equilibrium. That's our lesson. So 3 learning objectives, 2 understand, so it's going to be tricky. Understand KC for heterogeneous mixtures. Number 2, be able to calculate moles at equilibrium and understand when moles or concentration. So, okay, so you guys have been writing down KC expressions now. We did that last lesson. I know that I haven't managed to get you guys, I haven't managed to get questions up. The reason being is, unless I start writing the questions myself, and I have been doing a lot of that recently, it's taking me an awful long time. And so what I figured I'd do is I'd wait till this lesson before I can give you a homework, because the homeworks now will start to incorporate many of these skills. So, okay, let's just tick off the first learning objectives. So, and I mentioned this briefly in one of my other lessons, and I had a hesitation, and I didn't need to, and so we just need to talk about this. So, can you just put heterogenous equilibriums? So that now, can I just point out that these are the rarities. These are rare. The majority of the equilibriums that we deal with tend to be homogeneous. I think it's reasonable for us to define this first of all. Yeah, we see this word a lot, and I've already given it to you, but it's just nice to mention it. The word hetero literally means same, and genus means phase. Yeah, hetero meaning same. Yeah, hetero meaning same. And genus meaning phase. Yeah, and you're going to probably wonder what phase is. And of course, phase is otherwise known as state. Yeah, so this is same. Oh, I've just got that wrong. Homo's different. Sorry, who's going to correct me on the chat there? Yeah, hetero means different. Homo means same. Yeah, so different phase or state. So the examples of this, an example of a heterogeneous equilibrium. And I have to work quite hard at these, folks. I have to work really quite hard at them. So we've got, I'm trying to think of a really good example of this. I can do one. H2SO4 liquid. On the chat, please. If you've got H2SO4 in a liquid state, what is this commonly known as? Yeah, what is this commonly known as? And that's now going to form. Now, the problem is, you see, what it's actually going to create is going to create this. Or gas. It's not in reality. What's going to happen is it's actually picking up water. It's actually what it's doing. Hydrogen sulfate. Yeah. I like it. You'd need a Roman numeral. Thank you, Dat. Dat's given me the correct answer, the bit that I actually want. Yeah, strong, Nikita. That's hilarious. Strong sulfuric acid. Lol. Oh, that's really funny. Yeah, so in this case, this would be concentrated sulfuric acid. Yeah, concentrated sulfuric. Yeah. It also has its proper IUPAC name in a liquid state is hydrogen sulfate 6. Yeah, you do need the Roman numeral. Yeah, and you guys need to be aware of that. Hydrogen sulfate 6, because the sulfur is in a +6 oxidation state. Right, and then it's forming gaseous sulfuric acid. This is, by the way, concentrated sulfuric acid is kind of otherwise known as fuming sulfuric acid. This is a common name. And by the way, you need to be careful with this fuming sulfuric because there is another chemical called fuming sulfuric acid, which is oleum. Oleum is another substance which actually gets the term fuming sulfuric acid more. It's called the fuming means it's giving off vapors. Now, sulfuric acid does give off vapors, but it's more of a reaction with the water in the atmosphere, really. But the molecules are actually still evaporating, and then they're reacting. So hence, because otherwise you wouldn't see this. This should be invisible. Yeah, gases are invisible, but it's reacting with the water in the air, forming clusters of droplets, which looks like clouds, so fuming. Because it's not the weak one. Oops, lol, Nikita, that is the funniest thing I've heard in ages. So, okay, if we were going to write down, now, by the way, this is going to, of course, be in equilibrium. Sorry, I've done that as unidirectional, and it's not. This is in equilibrium. Now, if you were going to write down the Kc for this, there's a nota bene. So, a quick nota bene on the side. Yeah, nota bene. In heterogeneous mixtures, heterogeneous equilibriums, heterogeneous equilibriums, liquids and solids do not appear in Kc. The reason being, of course, is because we know that in Kc we are using concentrations. If anybody wants the understanding of this, I'm happy to give it to you guys. Yeah. We know that a Kc expression is concentration of products over the concentration of reactants. And if something is in a liquid or solid state, it has a concentration of 1. Yeah, there is no concentration because it's not dissolved in water. Gases appear because concentration is the same as pressure in a lot of ways. It's the particles per unit space, so it does appear. We'll come into Kp soon, by the way. That's next lesson. We're doing Kp, but I need to do this for Kc first. So what that means is with this nota bene, we can now create the Kc for this equilibrium, which will be Kc products, yeah, which is going to be H2SO4 gas, yeah, over 1. Yeah, so you're not going to get, the liquid just won't appear. Yeah, it's also to the power of 1, of course, so in reality it just becomes that. Yeah, I mean, everyone knows that. I've just done it over 1 to show you that it is actually appearing. And that number 1, remember, is its stoichiometric power. Yeah, equation, stoichi. And it flips it round, doesn't it? Stoichio number, which is, if you want me to highlight it, that number there is the number in front of it there, which is an invisible 1. So just to let you know, products over reactants, liquids and solids will not appear in a heterogeneous equilibrium. Now, people now go, why do you need to state this hetero? Now, I'll show you this, because if you have a homo, yeah, if you have a homogeneous equilibrium, yeah, same phase, homogeneous equilibrium, and by the way, there is one example you truly need to know because it comes up in all the practical questions, yeah. If we have liquid acetic acid, so glacial, this is pure ethanoic acid, yeah, otherwise known as glacial ethanoic acid. It's called glacial because it forms big giant crystals. Glacial ethanoic acid, which is a liquid, plus pure ethanol, which is a liquid. Yeah, you can establish an equilibrium to form an ester and water. Yeah, you're going to form an ester, which is a liquid, and water, which is a liquid. L. Now, because this is a homogeneous mixture, Yeah, because it's a homo, you then now get a full Kc with everybody in it. I'm just going to label this as ester, label this as water, label this as acid, label this as alcohol. Just it saves me the hassle. So we've got ester to the power of 1 times by water. Now you realize now this is a clever one. Water does appear in here. Water. Why have I switched to symbols if I'm going to do that? Water, acid, alcohol. Hopefully people are going to say, how can you get the concentration of water? Now, this is what I meant in my third learning objective. This is my third. Yeah, understand when moles or concentration can be used. Yeah, in this particular scenario, they're all liquids and it's a 1-to-1-to-1-to-1-to-1, which means in this particular circumstance, you would not actually be using concentration. Yeah, this is a nota bene that goes on here. Nota bene for these particular ones. Yeah. Nota bene. Moles can be used. Moles, not concentration. Used here. The reason being is they're all liquids. And because the ratio is 1-to-1-to-1. So you can use moles directly. Which is kind of nice that. Put that in a box as well. This one here, I need you guys to actually flag up. Yeah, this one actually, you need to learn this. It comes up on every paper 6, pretty much without any failure either. It's been on every A2 paper I have seen since I started BSKL. Every one of them. Unit 6 heavy. Yeah. Every one. You can look it up if you like. Look through the papers, they're all there. Okay, let's look at another example of equilibriums that are heterogeneous. Let's go for hetero equilibrium. Hetero EG2, got to work quite hard for these. Let's go for, trying to think of really good examples of this. Oh, I can't think of any. Hang on a sec. I'm just quickly Googling it, folks. I just want to have more examples that are actually really good ones. Oh, that's not an equilibrium. That's a joke. That's a terrible example. Oh, that one's a nice example. Okay, EG2. So number 2 is, I'll just star it, PCl5. Now PCl, this is phosphorus pentachloride. Yeah, and this is a solid. Now this decomposes at room temperature. PCl5 is a very unstable reactant. And it forms PCl3, phosphorus trichloride liquid, and of course chlorine gas. There we go. So in this heterogeneous mixture, what's the Kc value going to become? Can you put it on the chat, please? Put it on the chat, please. That was a good one, that wasn't it? Like that. Oh, funny. Trying to find more examples. Has everyone vanished on me? Come on, guys, get it on the chat. Get it on the chat, lads. Come on, peeps. I guess I should probably write down some more of these examples. So EG3, I should be able to come up with all of these out of my head, but yeah, it's not very easy. They're not very common. This is kind of like more of the exceptions to the rule, really. Oh, come on, Toby, rack your brain. Production of hydrogen, H2O gas plus carbon solid goes to, in equilibrium, of course, goes to carbon monoxide and hydrogen. Balance the equation. Oh, it is balanced. Lol. Carbon monoxide is a gas, and hydrogen, of course, is a gas. Kc for this one, please. Kc equals. You can see what I'm trying to do here, folks. I'm just getting you guys. There we go. Thank you very much, Donna. Yeah, thank you very much, Ria. Tenzi, thank you for contributing. Appreciate it. Yeah, it just becomes Cl2 to the power of 1. That's it. Nice and easy. What about this one? Give me this one, guys. Yeah, have a go at this one. I'm not entirely sure why you've given me that symbol, Emma. Don't really quite know what that means. Lol. Ooh. Do 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 do. Trying to find other ones. Trying to find ones that you'll have said. The phosphorus triiodide. That's another one, but that's the same as the phosphorus trichloride one. It's the same thing. Trying to find you other examples. I'm trying to find you some exam questions. But they are there. They are around. Solutions. Yeah, that's an interesting one. Yeah, that's a very interesting one. There's the concentrate. Yeah, dissolving ones. Dissolving ones are pretty good, to be fair. Yeah, so we've got EG number 4. Could do dissolving. Let's do to partial solubility. Let's go for calcium hydroxide. Calcium hydroxide solid, dissolving in water to form its ions, plus 2 OH minuses. And these are both aqueous. What's the Kc for that bad boy? Yeah. That's a nice one, because now the big numbers apply, don't they? Yeah. Nice. Wait, Mr. Duncan, just to clarify, we can use Kc with moles instead as well, which would allow us to include non-gases in Kc. No, Ben, it's not about whether or not they're gases or not. The only time you're allowed to use moles in a moles directly and not concentration is when the equation is uniform, 1 to 1 to 1. Yeah, I don't like it being in black. I want to do that in a different color. When these guys are all 1 to 1 to 1, you can use moles directly because you've got the same number of moles on this side as you do on this side. Yeah, so because it's the same, you can use moles directly. You don't technically need to convert to concentration. That doesn't mean that they won't make you do it. You wouldn't really do it unless you really don't have the value. The questions actually stand out a mile, Ben. It's a good point. They'll give you a volume, you see, in the question, and it stands out a mile. You'll see these when you start looking at questions. Well done for giving me the other one, guys, for the next one, which is nice. So this one, of course, the carbon's not going to appear. So products, yeah, over product concentrations over H2O concentration, yeah, all to the power of 1. So the carbon no longer appears. This one's much more entertaining. Yeah, again, oh, by the way, sorry, that's a solid, apologize. So Kc for this guy, did I just do that in red? Didn't really mean to do it in red, it's fine. Yeah, Kc for the next one. So for solubility, Kc, products, OH minus to the power of 2. That's the point I'm trying to make there, guys. Yeah, it's saying that the stoichiometric ratio in the equation is the powers to which your reactants and products appear in. Yeah, and then this one, of course, doesn't appear. You're done. That's it. Wait, EG3 has the ratio all of 111. I see what you're saying, but no, it doesn't. It's got 2 moles on this side, Ben. No. You're right. It does. Sorry. Clarification. Thank you, Ben, for that. You've got 2 moles on this side and only 1 mole of gas on that side. What that means is you're going to have a change in the number of moles in total. Yeah. Remember, mass is conserved, but moles aren't. It's fragmented, and especially since carbon doesn't appear in the because it's not in the Kc, we've got 2 moles going on the top. You'd have to put it in proper concentration there. You'd need a volume. Yeah, that one you'd want to convert into volume. Does that make more sense, Ben? Well done, Ben. Good catch. Yeah. This is why I do need this feedback from all you guys with these questions. They're good. You make me a better teacher. You guys know this. Anyway, so that pretty much boxes off. That boxes off this learning objective, which is nice. Ooh, come on. There we go. We can tick off the first learning objective. Recognizing heterogeneous mixtures and how Kc varies with that. Right, now's the big one for today. Yeah, calculating moles at equilibrium. Yay, right. Okay, guys. Right, calculating moles at equilibrium. Moles at at equilibrium. This is what I just want to do. Moles at equilibrium. Right. Now, in order to do this, I needed to show you some questions. Yeah, and trying to make these up is really tricky because it's very easy to make an idiotic mistake, but I'm going to give it a go. If I make a mess of it, I apologize, but it's good practice for me to do this, and I'll show you why. So question number 1, and it's hard to teach this without an example. So question number 1, if we take an equilibrium, and let's keep it easy, yeah? Let's say we've got SO2 plus O2. Let's go for some equilibriums that we recognize, yeah? This is the contact process, yeah? Do you know what? Suddenly realized I want an easier one. I want an easier one than that. Can I think of an easier one than that? You must be able to think of an easier one than that. Yes, I can. We've already used it. Yes. Okay, hang on. Can I use an easier one? Hang on. So they all have to be in the same phase and 1:1 in the mole ratio, the same number of moles on either side of the equation. It's not really so much with the ones. I know I said that just to clarify. Yeah, it's not so much really the numbers in front. No, because you can have two. It's really to do with the number of moles on. Okay, so hang on a minute. I don't want to use those examples yet. Right. You here in this example in EG number 2, do you use moles or concentration? On the chat, please. Moles or concentration here, because the problem is it's a 1:1:1, which I'm about to use. 1:1:1, but can you use moles or concentration? The answer is concentration. Yeah, you can't use moles. You can't use moles because I've got 2 moles in total on this side and only 1 mole on this side. Yeah, so you have to use concentration. Yeah, let's look at the next one. This one, 1 mole of gas on this side, 2 moles of gas on this side, we're using concentration. Yeah, what about this one? 2 moles of concentration on this side, 0 moles of this is concentration. Yeah, for this, all of them here, all of the examples I've given here, this one you can use moles because it's equal moles on either side. Yeah, I hope that clarifies. It's my bad. Didn't do that very well. I apologize. So I'm going to use some of the equations we did before. So PCl5 decomposes in equilibrium towards PCl3 and chlorine. Right. Now, what we're going to do is we're going to do a thought experiment. Good old Einstein. We're going to do a thought experiment. Now, this one is a solid, this one is a liquid, and this one is a gas. Okay. So what we're going to do is we're going to put in 5 moles. The problem is I should really have chosen. It doesn't actually matter really for calculating moles. It doesn't actually matter the Kc value. The moles doesn't matter on heterogeneous or homogeneous. You still have to use the same as. Yeah, so 5 moles went in, and this is initially. This is the start of the experiment, initial. So, and this is how I need to teach this. So in an experiment, we have, so this is our experiment. I'm going to do this in a different color. I'm going to go to black again. So in our experiment, we're going to set up our box. Yeah, we're going to set up our box, and I have to put a lid on it because it needs to be a closed system. Yeah, needs to be a closed system. So let's make sure it's closed. Yeah, got a lid on it. I'm going to add 5 moles of solid PCl5. That's what I'm going to add. Yeah, 5 moles of solid PCl5. Phosphorus pentachloride. What we're now going to do is we're now going to start the stop clock, and we're going to wait. Now, during this time, yeah, this is now time, ... Yeah, we are waiting to establish, waiting for equilibrium, because we know it takes time. Waiting for equilibrium to establish. Yeah. Now, and then at a given amount of time, what's going to have happened is in here now is we've got less PCl5. Yeah, we've got PCl5 still there, but we've now got gaseous and a little bit of liquid. Yeah. This is where I zoom in on this to make this a bit clearer. Let's color code this. We've got solid PCl5, yeah, and then we have liquid PCl3, which will be accumulating nearby, and then we've got gaseous chlorine in here as well, which is of course green. So we've got gaseous chlorine. So after a set amount of time, equilibrium will be established. Now, what we're then going to do is we are going to then, so this is classed, this is always the process. You have initial setup, initial brackets, starting moles, and then what you have is final. I don't really like the word final. I prefer equilibrium moles. Equimoles. This is end moles. Balanced moles, starting moles, end moles. Yeah, when it's reached equilibrium. Yeah. Now, what I always tend to also mention is change. So it's a rather odd thing, this. Let's now have a look at this example that I've created. I'm now going to tell you that, and let's turn this into, I need to turn this into a table. We've got initial moles, and of course, in the initial, we always know that we've got 0 and 0 of the products. By the way, there are set scenarios where they aren't 0, but usually it's 0. Now we've got moles equilibrium, equimoles, yeah? And I'm going to tell you that there is 2.1 moles of chlorine gas. So here's my question to you guys on the chat. What's the moles of PCl3 at equilibrium if chlorine is 2.1? What do you think the moles would be? Just for PCl3. I don't want to think about PCl5 yet. We're starting off with an easy example and it'll get harder, by the way. So what do we think the moles at equilibrium for PCl3 would be? Start off with an easy example, steadily get harder. 7.9. Dana has gone completely nuts. I don't know. You've gone, Dat, well done. Dat's on it. Tenzi's on it. Well done. Dana, you've gone nuts. Remember, moles is counting particles, not Ishkayan 2.1. Nikita, well done. Remember, Dana, moles are counting particles. Imagine you've got one particle of AB. Yeah, 1 mole. And it fragments at equilibrium. Actually, hang on a minute. We're going to have to draw 2 of these, aren't we? At least AB. Yeah, these are our initial moles, and it's going to fragment into A and B in the equation. Yeah, like this. And if I start off with 2 moles on this side at the beginning, 0 and 0 of A, yeah, if I just get rid of that for a minute. If I start off with 2 moles of A and B, and at the end, this now splits up to form 1 mole of B. Dana, would you agree you must, because of the way that this is decomposing in a 1-to-1 ratio, I must also make 1 of A? Yeah, I'm going to make 1 of each of them. And this one's going to decrease by 1. So there's going to be 1 mole of that left. Does that make sense? So that was probably not very well explained, to be fair. Once you start seeing, it's all maths. It's all maths, really. So you're right, because this is a 1-to-1. Okay, I understand. Good, thank you. That's great. Because this is a 1-to-1, I'm going to make 2.1 of these. And here's the next question. What's PCl5 going to now become? Now that I gave a quick explanation, what's the PCl5 going to become? So rules. We now need to establish some rules for this. So reactants And the problem is I need to actually give an example. 2.9, Donna, you're on it, is the right answer. Well done. Because this is a 1 as well. One of those will become, so they're just going to decrease by that same number. Put that in green as well. Well done. 2.9. Well done. Spot on. Absolutely right. Thank you, Donna. Donna's on it now, you say. Yeah, I like it. Good. Totally get it. Right. So what we now need to do is we now need to look at this from a more general perspective. Yeah. So let's imagine, let's give ourselves an equation. Let's do A goes to B and C. I know that this doesn't really make any sense in chemistry-wise, but I'm just trying to keep it as simple as possible. Yeah, what we realize is going to happen. Yeah, and in fact, let's make C2 for fun. What this now means is, if we have initial moles, and by the way, you have to be in moles. You can't use concentration in this setting. Yeah, initial, then we're going to have equilibrium moles. I'm going to have to fit it in now. I've done it now. Equilibrium moles. And I like to then do change moles as well. Change. So what we realize is if initial moles is X, yeah, initial moles is X, B and C will most likely be 0. Would everyone agree with that? Yeah? Right, what's now going to happen at equilibrium, we know facts. So the reactants will decrease. We know this. I'm going to put this in red here. Reactants decrease. What that means is you're going to lose moles. Reactants, nice one. Reactants decrease. Products will increase. That's an important thing to note. Just first of all, products will increase. Well, let's imagine that the change of A, in this case, let's imagine the change of A is Y. Shouldn't really do, I should just do it in X's all the time, really. Change is Y. So X is going, this one is going to be X minus Y. Yeah. And this is, it's going to, because, and that there is the change in moles. Change. Yeah. So X is going to lose it. B is going to, so this would be B plus Y. And C will be C plus 2 Y's. Now, this is the strange bit here. Y is the change. Yeah, what's going to happen? The stoichiometric ratio in the equation decides how much it's going to multiply the change by. So now we need to put this, and I'm going to, by the way, this method, this setup is actually how I teach this, and you'll see this in a second. I don't really like the algebraic version of this. It makes more sense when you put this into questions. Let me show you. Right, this makes more sense, I promise. Right, let's choose that one. That one looks good. I just kind of want to take that, just that one, really. So, no, I just want to steal him. Oh, but they've done the writing for me. Nah, I'll do that. I'll take that. Ah, it's irritating. Just take him. Do them bit by bit, rather than all in one go, which is a bit messy. It'll make sense once you kind of get to it. I don't really like the algebraic version, but it actually has it does have value. So, right, here's your question. So what we now need, we realize we've got initial moles at equilibrium. Now we need change. And here's the genius bit, change moles. Can anyone see where the change is? Where can you see the change? On the chat, please. What is the change moles? Somebody tells us what the change is. Who is it and what's the number? It's a terrible table, isn't it? I just don't really need to divide it up, but I just see some value in dividing it up. Point 4, thank you, Dat. Yeah, the one that we can see is here. we can see that carbon monoxide has gained 0.4 moles. Right. Now, here's the great thing. That has a number 1 in front of it. What that means is this here is what I like to call change X. Yeah? So the change moles, 1X, which an X is the, or 1Y from my previous one. Yeah, 1X, which is the change, is equal to plus 0.4. Sorry, is equal to 0.4. What that now means is I can now apply that to everybody. So now that I've got that, would anyone like on the chat to guess what the change is going to be then for hydrogen? You realize that everyone's now going to be able to do this probably quite easily, because this is where my little algebraic bit comes in. C was 2 Y's. B went up by 1 Y, 1 change, 1 X, 1 Y. This is now going up by 2 Y's because of the rate. Ah, you see, she's already got it. Thank you. Thank you, Dana. Thank you, Jasmine. Well done, they've got it. It has a 3 in the equation, which means I'm actually going to go up by plus 1.2. So the great thing is, because it started at 0, there it just becomes 1.2. So the next question is, what do these guys, of course, gain their X multiplied by their ratio. Yeah, let's call this change X. This is X times 3X. Yeah, let's just do 3X change. This is a 1X change, and this is gain because they're products. What are these guys going to do? Yeah, and the great thing is they're a 1-to-1 and they started off at the same value. This makes it really easy. This is a nice, easy example. Yeah, these guys are going to lose 0.6, right? Because this guy is a 1-to-1. If the change is 0.4 over there, what that means is this is going to be a minus 1x and a minus 1x. And that 1x is equal to 0.4. So they're going to be 0.6 and 0.6. And there's my moles at equilibrium. Do you see what I'm trying to do with the whole like algebraic bit? I know I'm not particularly good at it, but there is some value in it. I can't really explain why I know there's value in it, but I do, because students sometimes kind of latch onto this and go, actually, I kind of understand it from an algebraic perspective rather than me just trying to teach this via numbers. Yeah, you can teach via examples on this, and some people prefer it, some people don't. Let's go to the next one. Let's go to question number 2. In fact, okay, guys, here's what I'd like you to now to do. I'm going to have no more conversations with you. There's only 15 minutes left of the lesson. We have already done this one. Can everyone now pause the video, and can you do questions 2, 3, and 4? Yeah, this will probably take you about 3-4 minutes. Yeah, and then you can unpause the video and check to see if you've got them correct. That's all I want you to do. Fill in these tables. Yeah, and then by the time we'll be close to the end of the lesson at that point. You don't need to contribute on the chat any longer. Okay, so when you're ready, unpause the video. So what I now do is I look at question number 2 and I go, well, that's a 1 there. So that there is going to be a minus 1x because it's got a 1 in front of it. And the change that it's had there is minus 0.03. That's a clever trick, isn't it? Yeah, that one's dropped. So this is my x value. And this is actually 1x to boot, which is quite nice. 1x equals 0.03. So if nitrogen is dropped by that value, by the way, I always like to check these things. I know I'm right, but 0.1 minus 0.07. Yeah, 0.03. Right, hang on a sec. This is where I need to shrink my pen massively. As small as I can go. That there has lost 0.03. This one is going to lose 0.03 multiplied by 3, its stoichiometric value. 0.03 times by 3 is 0.09. And then I go 0.1 minus answer. So I'm going to end up with an equilibrium moles of 0.01 of that guy. Sorry that it becomes really hard to see. There you go. Right, this one's going to gain by 2x. Yeah, it's going to gain by 2x. Well, what was my x? 0.03. So 0.03 times by 2, 0.06. Add it on. The final answer is 0.06, and I'm finished. Yeah, tick. Next, okay, so this one, once again, they've been nice. These are easy examples. We'll keep going with these as long as I've got the time to do it. So the great thing is this one here has decreased. It's dropped by -7, and it's got a 1 in front of it. What that means is 1x equals 7, right? That one is also going to drop because it's on this side of the reaction. So that's also going to drop by 7, yeah, and therefore that's going to equal 3 as well. This one's got a 2 in it. So this one's going to gain 2x. Yeah, and if x is 7, that's going to go up to 14, and I'm done. Yeah, next. Once again, that one there has a 1 in front of it. So the change, 1x, which is the change, is going to be 0.2. So the water's going to increase by 0.2 as well. That's going to drop by 3x, right? So that's going to be 1 minus 0.6. That's going to end at 0.4. And then this one's going to drop by 1x because it's got a 1 in front of it. So that one's going to drop to 0.8. And we're done. So this is just a game, folks. It's just a game show. That's all it is. Now, this brings, let's just quickly understand what moles of concentration. I have talked about that, and I think we're okay with that when the moles on the equilibrium are the same on both sides. And that actually brings me to the end of my learning objectives. Yeah, and we've done 4 examples here. They're going to get harder the more you do them. And once you finally get to, by the way, the process is the same. Yeah, and once you start getting to real exam questions, and I'll post you some today, you'll be on it. This is not a complicated matter, just takes a little bit of effort. Yeah, okay, I'm actually going to leave you be there, guys, today. And what I will do is I will post for you some questions on the classroom today. It's going to be more of these. I'm going to post you 2 sheets of this because it shouldn't take you very long to do. So I'm going to post those. I'm going to end my lesson here. Guys, it's been great to see you. I hope that all made sense. I'll set the homework on the classroom now since we've got 10 minutes to go. And I'll see you all very soon for our next lesson. See you later, guys. I'll see you all in school. Wednesday. Excited. See you later, guys.